So as you are aware that vision transformers, they came in some years back, a few years back. It was released by the Google, and it just very quickly it just hyped up because it didn't apply any CNN layers inside it, and with just the help of some linear layers and some attention layers, it was able from the CNNs on. But we investigated that there were certain problems at the main problem was that it needed a large amount of the data to train. So we thought, like, if we can find a way to just train the transformers on small data sets. So what we do usually is, for example, we first train the vision transformer on a very big data set, for example, ImageNet, of 1.2 million images. Then we transfer this vision transformers to some other set of data which has small number of images. It's the usual trend that we follow. But the main thing is, why can't we train the vision transformer explicitly on the set? That is the thing. That's we this research. So research I did at while I was a research assistant at Mohammed bin Zayed University of Artificial Intelligence, and it was a collaboration between us three people. He was my supervisor at that time, and Muzammil Nasir was a scientist here, and first author is me. Let's go on first, the motivation part. So as I said, that vision transformers are hungry for data, and they need large scale. First, you need to train them first on a large scale data, for example, image. You can transfer that ViT to small data sets. So actually, so for example, in the CNNs, you have the locality and inductive biases, because we apply some kind of filters in the CNNs, and with the help of the filters share the weights between between them, but like there is no filters the ViTs, so there is no weight sharing mechanism inside the vision transformers, and because of thing, what happens is that they lack the inductive biases which are inherent in the CNN features. So this is the second problem. The third problem that we investigated here was the weight initialization. We found that if you do not initialize your ViT with appropriate weights, it may converge to very different solution. So as you can see these figures here, on various initialization schemes, for example, uniform, Xavier uniform, a few more techniques here. And we trained some 3 versions of the ViT. One is the ViT normal ViT, other is the swing ViT, other is CAIT. And with each transformer architecture, we observed that as you change the initialization scheme, the solution, the accuracy, the final accuracy is really different. And as you can see that for each of these initialization schemes, the transformer does not have a very constant accuracy. So this by far was the third issue that is in the vision transformers, which motivated to find a better initialization scheme for the ViTs to work on the small scale set of data. As you can see here, this scenic image, they all are data sets as in terms of the ViT architecture. So next, I hope it's clear up to now.
I think it's definitely from me at least.
So I think I should move forward. So what exactly? So that I was talking about that we need to train the ViTs or the small data sets, and we identified some small data sets like CIFAR 100, Scenic, SVHN. Although they have like 90,000 images, 50,000 images, but it's still less for the yeah, to exactly train them very. And also one of the aspects that we saw in this paper was that if you have the image, for example, if we train the model first, we resize it to larger sizes, for example 512 cross 512 or 256 cross 256 or something like that. But we didn't. In this research, what we did was we tried to save the resources. We tried to reduce the amount of the resource that that goes into the training of these big architectures on very big images. We kept the image size very small. For example, for the tiny image, we only resize the image to 64 size, for example 512 cross 512. For the and SVHN, we kept the sizes similar to what their original sizes was. We did resize the images here. The main reason was to make these architectures work on small images, also smaller in terms of the sizes, and also smaller in terms of the number. So it was, for example, like before, we never trained. If we trained a model on very small images, we would of course get a very low accuracy because larger images help. So in this research, what we also saw that what we also did that we managed to train the ViT on low resolution images, for example these. So I think should move on to the methodology here. And our method is based on matching the local and the global views. So before going into the methodology, let me give you a brief overview of what is what the ViTs are. So the ViTs, as you can see, they have a global attention. They attend the image as a whole, while as the CNNs, they attend only a small part. They are very good at the locality, while as the ViTs are very. So the CNNs lack the global attention, the ViTs lack the local attention. So in order to train the ViTs on the small data sets, induce some kind of the locality inside the ViTs. That, for example, if we have an image whose height is h and width is w, we take some local crops. As you can see, we took some 8 local crops here from various regions of this image, and we took some 2 global crops, which kind of contains the maximum information in the. And we resized these images to the half of the original image sizes, for example h by 2 and h and is width by 2, and to their original sizes, that's w. And we use certain global and local ratios here because we found that if we do not make appropriate global and local, the whole training may collapse. So I think it's for since up to here it's clear to everyone what's going on.
I think that is kind of to overview it. Them from the image and small
Yes.
corps local views originally, and you are resizing it to h over 2 and w over 2.
Yes, exactly.
And I see you are applying some random transformations as well, like
exactly.
hue. Okay. And,
yeah, the gray and this, yeah, exactly.
And you're picking up, cropping some bigger portion of the image actually, and you are resizing it back to H and W, and you as well seem to apply another sort of transformation as well.
Yeah, exactly. So we apply some kind of the augmentations to both of these local and the global crops, and the local and the global ratio we choose very carefully. Like we change from example some L1 to L2 for the local and some G1 to G for the global views, but we have also done kind of the ablation studies which go into choosing like what should be the appropriate local and the global ratio that we'll talk about later.
So is this ratio represent like the ratio of cropping for either the
Yes.
local view and okay.
Yes, exactly. So they are actually the ratio of the crops that you can cut out of the image.
Okay, I think that's cool.
Okay. So let's move on to the next phase of this. Yeah. So what we do first is we find if we do first some kind of the self-supervision with the same data set that we have, this is the image from the small, some kind of self-supervision, it may help the ViT to have the better weight initializations. But the one catch here is that other approaches, they first do the self-supervision on some big data set, and then they smaller data. Here we assume that we do not have like big data set available. So the same trained data, same trained small data set that we have, and we do the self-supervised learning on that small data set first. As you can see, if we have given image X, we take some local and the global crops out of the student-teacher strategy here, where student is also a ViT and the teacher is also a ViT. So what we do here is first is that we pass the local views to the student. Also, we pass the whole global views inside the student, but on the right side, as you can see, the teacher, it only gets the global views. So we believe that in this format, this whole teacher can guide the student to learn better. Pass local views to the student, we get the features of both the global and the local views which are represented by FXG and FSXL. That is the local views from the student, and the global views. That is the features of the global. Also, from the teacher, we get the features at the end. That is FT of XG, which represents features of the global view from the teacher. Now, after this, it's important for us because we want to match the features with the teacher. Since student also has the local views, so the student has some kind of the locality, and the teacher only gets the global views. So the teacher. And as you can see that we are trying here the self-supervised view prediction. We are trying to match the features of this teacher with the student. We exactly trying to match the global views coming from the teacher to the local views which are coming from the student. And the loss function that we have employed is on the right side, which we call as supervised view prediction objective. What exactly is happening is that it is trying the global views with the local views, because as I said earlier that the ViT lack the locality. So in this way, we're trying to induce some kind of the locality inside the ViT by matching the global views coming from the teacher with the local views from the student. Any questions up to this point?
So I actually had a question. So the teacher itself is trained on a separate data set, or is it actually being trained alongside the student? Or
so the teacher, both the student and teacher initialized from the scratch. There is no training at all here.
Okay, so it seems that you are having a signal that is showing the gradients from the teacher. So I was wondering how this.
Oh, exactly. Oh, actually, I'm yet to explain that part. So yeah. So the function here, as you can see on the right, we update the student with the usual gradient descent method. So this loss, we take the gradients of this loss and we backprop that loss inside the student here. However, we do not train the teacher here because we have applied some, as you can see, we have applied some stop gradients here. That means the gradient loss to the teacher. So how do we update this gradient then? We take the exponential moving average of the weights of the student and we pass that inside the teacher. So the teacher is getting the exponential moving average of the weights of the student here. So whatever the student is learning here, since all the epochs, it's being passed to the teacher. So at each epoch, we calculate the self-supervised loss here. We pass gradients of the self-supervised loss to the student gets updated, and then we take the exponential moving average of the student weights and we pass that inside the teacher. I hope, Amar, that's clear.
Actually, it is. So you are training the teacher from the exponential moving average from the trained weights of the student itself. And okay, that sounds good. I have actually a question regarding that. If you might go through the notations you are using just to get a little bit of sense.
Okay. So that's the notations are very simple here. As you can see that FGT is the global features that are coming from the teacher. That's this one. FGS are the local features which are coming from the, they are the features of the global views that are coming from the student here, like this. FSG. FGT, as I explained, are the features coming from the teacher for the global views. And FLS are the features of the local views which are coming from the student, this one. And okay, so, I mean, that is because, I think that is because we are passing both the local and the global views inside.
Oh, I see. So the student itself is propagating both some global and local features along with each other, although the teacher are fed only with the global view, right?
Yeah, the whole teacher is only fed with the global views. That's it. Okay.
So now EMA, the moving average of the weights of the student. Yes. You are actually doing this with the weights of the global view only of the student part, or what are you actually doing? And I have another question maybe later on regarding what is your intuition, or why did you think in first place about doing that thing? That might be interesting.
So if I understand, so if I understand your question properly, you mean that what I mean, kind of, what is this kind of FGFS, or what are the features of local views from the student or the global views from the student? What are these actually?
Yeah. No. The point is that you have so the students was the global and local features.
Yes, exactly.
Right? So and the teacher is only propagating the global features.
The global views, exactly.
So you are actually feeding the weights of the teacher, or actually training it from the moving average, the expected moving average of the weights of the gradients of the student. So my question is that in the moving average, are you computing it to that is primarily focused on the global view only, or are you doing it for all the weights of the student architecture? Like the student architecture have mainly two parts. So if you you have one portion of weights that is responsible for the global view, another weights. If I'm understanding correctly.
Yeah, so I got your question right. So the exponential moving average, when I'm calculating it for the entire for all the weights. So I do not have any sort of separate weights for this for the local or the global views here. So I'm just calculating it for the entire student network.
Oh, okay, I get it. So now regarding the other question is that I am actually thinking of what might have led you to do so, or what was your intuition in doing so, or this is a base idea when you just tried to do so?
That's because exponential moving average it takes into account all the information that went into previous epochs. For example, exponential moving average of first epoch, it will only transfer the information the model learned. After 10 epochs, it will transfer all the information that the model has learned from all those 10 epochs. So the teacher is getting information of the student of his past also and his present also. So kind of that is for the teacher. It is able to guide the student because it has information about the past updates also and the current update also. That's what the exponential moving average is doing here.
I know you have another meeting. I hope I'm not really consuming your time. But if we have enough time, so why in first place stopping the gradients from those teachers?
So that means I am not passing the whole gradients inside the teacher, because my motto is here: the student will be passed in the teacher using the average of these things. Because I can explain later what we are doing so, because we are, I mean, we got inspired by this paper as is mentioned down here. This exactly is a paper which was released by the Facebook. So they were doing some technique and it worked for them. And it worked for us also in terms of the small data.
Okay, I think that is kind of cool. We can.
Can I ask three simple questions?
Yes.
Yes. I have three inquiries. The first one, why is summation? So is it based on every global view image has several local view images? So we are trying to calculate the loss for all the local view images for this global view image. This is why summation is.
Yes, exactly. Yes, exactly. So what is happening here is that we are trying to match each local view with each global view. So that's why.
Second question is, why don't use a large pre-trained model for the teacher and stop any gradient flowing through it and optimize the calculations a bit more?
Our main was that we do not have any big data set available, any big model available. It's like here that have a model. How can you extract the maximum information from this model on this small data set?
Okay. The last question: what is the dynamic position embedding? Is it
so dynamic position embedding? So that means, for example, as we saw in the last slide, that the size of the global views is h and w, and the size of the local views is h by 2 and w by 2. So in order to handle these size differences, we have employed some kind of these position embeddings, which kind of interpolates if for example our ViT takes the size of 220 of 64 cross 64, okay, and my local views in that case will be only 64. So how to handle the transformer? So for that, these size mismatches, we have employed this. We had to employ this module here.
This makes sense. That's all for me.
So we'll move forward for this if everyone is fine. So next stage, when we are done with all this supervised learning, we have also has learned some weights, and we have a teacher using the exponential moving average at each epoch. So we experimentally we found that. So then the next stage is, for example, if we did the self-supervised learning, then we do the supervised learning data set. Now, if you see the second stage of this on the right side, we transfer the weight of the teacher to a new VI, and we do a supervised learning on the same test set, our model on a new test set. For example, SIFAR, we first do the self-supervised learning on the on the train set of the CIFAR-10, that's this. Then we do the supervised learning of the same data set on the training data with the weights of the teacher, and we test the model on the test set of CIFAR-10. Because it might be a bit confusing here. The thing is, only thing involved in the self-supervised learning and supervised learning is the training set, and the testing set is separate. So once we are done with both the processes, we test our model final represented in light blue on the any question. If we have
So just to my thoughts, you are actually trying to fine-tune the teacher architecture the same in your
on the same training data set. Exactly.
And then you're evaluating on the test or something, right?
Exactly. You're
okay.
So first you do the self-supervised learning set with this method that I explained in the last slide. Then when you have learned the weights of the student and the teacher, we only take the teacher model, we transfer it, and we fine-tuning of the again of the same training data set, and then we test our model on the test set. So as you can see, for the fine-tuning, for the supervised fine-tuning, we simply employ here, as you can see on the right, because where yi is the actual of the image and fxi is a predicted label from this. I hope this is clear.
It is for me.
So if there are no questions, I can move forward. I hope this all strategy is clear. First, we do the self-supervised learning on the low resolution views. Then we do the supervised learning on the same data set. And then we take the weights of the teacher. That is and then we test our model on the test set. So if that is clear, we can move forward with this. As you can see that we calculate the top one accuracy here of the models. As you can see that these are the models that we used. The ones shown in the magenta color are our approaches. As you can see that on every data set, our model has higher accuracy than the base. So first we compared, if you see the first we compared against the resident. Then in the second row, we compared against SLVIT, and it was in NeurIPS paper last, 2 years back. And as you can see, that consistently outperforms the other approaches on almost all the. Yeah, so our model, so this makes us believe that our model, first thing is that against any ViT architecture in these student-teacher modules, we can any ViT. So our approach is model agnostic here. And second thing is that we can outperform the existing methods which try to train the ViT on the small data sets. I hope that these results are clear to you.
This actually is amazing. How many of the other architectures are trained with augmentations on?
So for now, that time we only trained with the 3 variants, ViT and Swin ViT and CL. But I think since I mentioned here some time back that our approach is model agnostic, so you can use any ViT architectures in this method. So there is kind of no. So if we move forward a bit, so this is kind of something we observed here. So when I hope this image is clear, because I couldn't most higher resolution. So you can see our ViT, which is represented in the column, extract maps out of the ViT for certain images. And we found that our ViT, that is on the last column, it has a better shape capturing ability. That makes us believe that our ViT it captures the semantics of the image really well. It captures the object of interest, because here in this image the object of interest was this for this, and you can see that our ViT methods, they also pay attention to other useless regions in the image, which is not desired at all. Compared to our approach here, you can see that our ViT only pays attention to this tower here. As you can see in other images as well, our ViT kept shape of the objects of interest here. As you can see in other approach are not able to capture the shapes. I have some more examples I'll show a bit later, but for now I meant to say that our super this learning, it brings about it just enables the ViT to learn these semantics really well, and we believe that this is important image class because the attention mechanism, how accurate is your ViT, it also depends on what the attention mechanism is focusing on. So if its focus is very dispersed, like in the baseline architect, like in these images, it won't be able to classify the images really well. But as compared to these images, if you see that our ViT architecture, which we drew our method, it is able to capture these small intricacies, semantics of the images really well, and it only pays attention to those objects in the image which are of interest. For example, in these images, the object of interest in this image was duck, so it was able to capture the shape of that something. It's a bird, so it was able to capture the shape of. I hope that's clear. Now this is a overall a general perspective of our approach compared to other approaches. So in this figure, we can see that our method as shown in this red circle not only has its highest accuracy on the tiny ImageNet, because this whole diagram is for the tiny ImageNet this set of data. Not only it has the highest accuracy on the tiny ImageNet, but it also has the lowest parameters. So what we did was, I will just show our we reduced the layers of our ViT architecture. So not only has it lowest parameter, but also our accuracy of our ViT is the largest as compared to lines on the tiny ImageNet. So x-axis here represents the parameters in millions, and the y-axis represents the accuracy. So as you can see that our method, it outperforms the baselines in terms of the parameters also, and also in terms of the performance. I hope this diagram is clear to you. Oh, thanks. So let's move a bit forward to this. So now, so it was a brief introduction of our research. So what we exactly showed that our is effective in training the vision transformers on set of data. Also that data is low resolution data set, and the number of the images are also less. What we propose supervised learning mechanism which induces a sort of biases inside VITs. And then when we are done with this, we initialize the net with the weights of the teacher, and we do a simple fine tuning on the same training data set without the requirement of any external large set of data. So through experiments that we show our method is effective, and it can serve as a better initialization schemes to train the VITs on small data sets. I think that's it from my side. But if you're supposed to run our code is publicly available at this. You can freely use it. But before going through this, I have to show you a few more things that I want to show you from my paper. I can open this here. Are you able to see my screen? The main paper?
Yes, Hanan.
So I have to show you a few more things that we explored. For example, the normal VIT number of layers is 12, but we only kept 9. Size used in the VIT is 16, but we only kept the patch size of 4 and 8. The dimensionality we kept 192. That's for the VIT tiny. Number of heads we kept the same as 12. MLP ratio for a normal VIT is 4, but we count, we largely reduced the parameter count of our VIT, same followed in other VIT architectures as well. So one more thing I wish to show you here is that yes, so we also tested our approach on the fine hard model, and that is aircraft and data set. Our model, it largely outperforms the baseline architecture VIT log, which was in groups. And as you can see that is baseline, it struggles to train on these set of data. One more thing that I want to show is here that we also tested our approach across the CIFAR 10, which is a version of the CIFAR 10, and CIFAR 100C, which is regarded as a corrupted version. They have added some kind of the corruptions in the image. And as you can see that our corruption accuracy or our corruption score is less. I mean, because lower is better in this case, our corruption accuracy is less than the baseline architectures, which shows that our model is robust enough to handle the corruptions in the images. Let's go on to some ablation studies here. One thing I would want to show here is that if we train our VIT only with 50% of data, or 25% of data, or 75% of the data, it's still other baseline architectures. Our method is here represented by the green bar, and as you can see that on all the data sets, CIFAR 10, CIFAR 100, and a tiny image, we train on the 50% of the train set, and we test on the whole entire test set. And as you can see here is that our model, it constantly outperforms the other approaches, even on the less data set, even on the images. Here, one more thing is that I told you that we are using the weights of the teacher, not the student. We did some ablation study, like which weights to use when we fine tune the model. So as you can hear is that this small table, we just did a small ablation on the 400 and the tiny ImageNet, and we found that the weights of the teacher were more effective for the fine tuning. That's why we initialize our model weights of the teacher instead of the student. More ablation here. What range of global and the local waves are you taking? So as you can see that we varied these number of the local, and we varied the ratios of the global and the local waves, and we found that what worked best for us was this for this value as I highlighted it. That's the local crop should be in the range 0.2 to 0. in the 70 to 100% of the original image. That's we got because at these crops we got the highest accuracy here. And same I have shown here. Next, in my paper, let me just go back here. So the question is, why the linear size of 1024 feature other sizes? For example, they're 512 or 2048 or 10,000 or 50,000 here. So as you can see, we did an ablation study. We also did an ablation study here, and we found that the size of 1024 is the best in our case, as we recorded highest accuracy across various these model architectures here. So you can say now you can hear that approach, why we didn't apply our approach on the CNNs. We tried to apply our approach on the CNN that result 18 with our initialization method. However, as you can see, that scores were not increasing on the CNNs. Now, you might ask why. That we are trying to induce the locality inside the ViT by our approach. But as I also mentioned here that the CNN already, if we try to use more locality, it won't help at all because the CNN already that knowledge, they actually need the global knowledge. So this method, our method is more effective on the ViTs rather than the CNNs. Also, you might also want to argue.
Sorry, Hanan, to interrupt you a little bit. Just do you have like before and after applying your method, like training resident from scratch, how it was performing on Cypher 100, for example, and after? I mean, does it stay the same, or is it going down, or
I
what?
think I have the ablation study that I did, and I think this is the thing. One sec. So we use some natural initialization methods, and we used our method, and we found that the increase was not very big. For example, from 64 only it went to 65 or something, and from 52 it just went to 53. That's it. So the jump was not that big compared to the normal. If we train from that, our approach may not be very efficient on the CNNs.
Okay, cool.
Okay, so you might also want to mention here that why you didn't use any other self-supervised learning method, why we had to come up with this local global matching sort of the self-supervised learning method. As you see here is that we tried with other existing self-supervised learning methods, MoCo V3, SimCLR. We tried to train them on the small data set as ours. However, as you notice that they are not very effective on the small data sets because the scores with our method were pretty large as compared to these methods. So that also kind of it proves that our method was kind of more effective. It is more effective on the small data sets. Next
question. I have a small question.
Yes.
Is your method sensitive to large models? So the ViT you showed up, its number of parameters is actually small compared to other models. So if the model scaled, we had billion parameters models. Is your
yes. So if you even use a large data set or large model, you might have to tune these parameters a bit. For example, what head size you will use.
But the method itself will still be efficient for large models.
It will still be efficient, but you might have to tune these parameters. For example, the size, the local and the global crops, or the head sizes. But it is scalable to large image data sets and also large models.
This is amazing.
One more thing that this approach, you might argue that you are using the self-supervised learning method, it's not a fair train this method, their method for 600. And it still didn't give us that much accuracy as we trained our method only for 300 epochs, half the number of epochs. So that would prove that our method is also efficient in terms of the computation, in terms of the time also. I also mentioned here that we use some 3 linear layers here. And you might want to argue why we didn't use 2 layers, why we went for 3 layers. And the answer you can find here. We try to train with 1 layer MLP layers, and the 3 layers in our case effective as we got some greater accuracy with when we use the switch from 3 layer. Also, as sizes here, we chose 124. We also what happens if we choose a large head 65,000 size. We argue that if you use a very size, your features might overfit on that, and you might not get the accuracy that you desire. As we experimentally, we showed it here.
Wait,
yes, sure.
Can the better results, the better numbers be because of the new MLBs, not the training methodology?
So, if you're talking about are you talking about the head size?
Yes, about the 3 MLBs in the end, because when you compare these methods, the ViT, the old ones, I don't think the old ones had the 3 layers in the end, the 3 added layers in the end, MLB layers. So can the boost in performance be because of these MLB layers, or the training methodology in itself is actually?
Yes, just because, as I mentioned, 65,000 is a very big number. So use this 65,000 because like your features might highly overfit these, as you might be aware about that fact. So we found that it affects a lot. Like in our case, if we do a self-supervised learning with 65,000 MLP layer at the end, it kind of largely overfits the features. That's why it's not able to perform well on the test set. So kind of this is a bit sensitive in this case. And if you are
the head size a little bit to make it focus more on the.
Yeah, I mean, compared to the head sizes here, it's kind of very less. Yes, because we like this number is very large, so we wanted to try what happens if you use a very large number in the approach. So kind of we found that sensitive to these large sizes.
Yes, the intuition is always that larger embedding size can hold more information, but
yeah. But the thing yes. I want as you see that in our method, the sizes of our image is very less, like 64 cross 64, something like that. And so the feature sizes of these will also be very
less. There is not a lot of information in these images to have a
exactly. So if we use size for a small information, it might overfit on that.
Yes.
Just one another point actually regarding your point, Muhammad. I think the 3 layers after doing the self-supervision of the extra using vision, it does it and get only the ViT model weights and it is then fine-tuning it if I'm remembering correctly.
So, exactly. So the weights are transferred only for the teacher model, not the linear layers. Amar explained it right.
Yes. So the linear layers doesn't come with us as a final.
No, the linear layer doesn't come here. Yes. Only the weights of the teacher come here.
Okay, right.
Here, these are some of the these ablations we did, and I want to show you some things that our method does very properly. So if we just do a self-supervised learning of ViT with our method, and you try to extract the maps images, you will find that our method, it kind of captures the attention maps very well for the shapes here. As you can see that it has captured the shape of almost every image really well here. Like the object of interest is here dog, so he has kept, so it has captured the semantics of the dogs really well. For here it's this, it's a deer, so it has captured the shape of the deer well. And here, as you can see that in all the images is the same. As you can see some more images here. So our method is kind of able to, so here we have compared with other methods as well. And as you can see that our method, it is able to capture the shapes of the images as compared to the other baseline approaches. And that makes us think that how that we can also with our approach on the semantic segmentation tasks. So I think that might be a nice future work for this approach. I think that's it from my side. If you have any questions, any queries, you can just ask.
I have one last question.
Yes.
I've read a paper maybe 6 months ago about the comparison between vision transformers and convnexts, the new version of convolutional networks. And it basically said that transformers has more robustness against corruption and stuff like this. But the new version of convolutions is actually achieves the same results as transformers through the optimizations that made the new version convnext. So I don't know if you know about convnexts, but I was wondering if it if in this efficiency targeting, if I can name it this way, is convnexts a good approach? Is it a simpler approach for training? Because your approach is a little bit complicated, I think. So what's your thoughts about this?
So the convnext paper was released by Facebook like last year, and as you can see that paper, if you just read that paper, they have done a lot of optimization stuff. Like for example, they have used certain layers. We use this layer. We we don't use this layer. They have optimized the parameters. What sort of parameters we need for this layer. So that's a very kind of exhaustive work that they have done there. And if you do the same exhaustive work in the ViTs, maybe like you can achieve work in the ViTs. That work was much, that was a very nice work, and it still showed us that are not dead yet, and they can be, if you kind of do some tuning, some kind of you choose the parameters really well, you place the layers very well, that can also help you. Like it's not like that may not, maybe if you do some kind of the things inside ViTs also, maybe that.
Okay.
So that was with the answer.
I think I got you on the so just actually move to another point, and when Muhammad is back, we might get back to this point.
I'm back. Sound keeps shutting down and on.
So my point is that it is actually a hypothesis. I'm not really sure about it. It is a nice piece of work, actually, Hanan. Congratulations for this. So my is that it is regarding the expected moving average, actually, of the ways. So it is I still actual intuition of doing so, and why is the teacher is better than the student? Because in teacher student, of course, the teacher is a better model, but you try to teach the student to be as well as the same, as better as the teacher. So one thing came to my mind is that with the expected moving average, you might be actually what is done is that you might be thinking of it as if you are actually in some different versions of the students across the time, as if you're training, because you know there are kind of doing some was one single training, like you get some snapshots of the model while you are training it, and you are actually ensembling the weight with moving average, and this typically improves the performance of the. So I'm not really sure about it, but do you think it is plausible
I think yeah, as you said, and as I mentioned earlier, that the teacher by exponential moving average, you're actually updating the teacher with the weight of the student up to that epoch. So all the information up to that epoch transferred inside the teacher. So the teacher knows what all student has learned until now, and kind of information. Also, how you are trying to induce the locality inside the teacher is that because the local views are getting passed inside the student, so the student has the knowledge about the local views, and by this exponential moving average, you are also transferring that local information inside the teacher. And what you said also like makes sense. That is also one of the reasons why the teacher weights are more effective than the student.
Okay, so another thing is that regarding the process of the training process of the self-supervision in particular, I was just thinking beyond the experimentation stuff, like I'm not like I'm not really actually able to phrase my sort of ideas into words, but the thing is that how were you sure that of course you mentioned that there is a nice paper that influenced your piece of work regarding this push, but I am just asking if you have any other intuition, like from reading the paper itself, because I have obviously not read it actually. But do you have any intuition regarding why this type of self-supervision might actually be working, right? Because initially you are not really starting off with any kind of mind or anything, but things progressing with training, although there is no initial training of the teacher or anything.
So the method of adaptation of the teacher. So online adaptation is a kind of a very established method that being used in also in SimCLR, that's being used in the Dino. So in these types of the strategies, you don't need to realize that strong weights or something. You can, because what our motto here is that you need to guide the student in an online fashion. If you already have a strong teacher, why not we use that teacher only for the classification? What you hear is that how can you learn a self-supervised objective and induce those some kind of the dynamic weight, very good weights inside the teacher network, because the weights of the teacher, because how you initialize the vision transformer also depends on what kind of weights that whole teacher has learned. So the what kind of weights it has learned, it comes from the objective you are using. Here the objective was simple, that you are trying to match local, and the hypothesis behind this goes that you are trying to induce the locality inside the ViT, and this strategy seems to be working to kind of apply this exponential moving average strategy, because as I said that exponential moving average, it transfers everything. For example, if you are at epoch 10, like you are doing a self-supervised learning. And if you do the exponential moving average of at epoch 10, you are actually transferring all the information learned from epoch 0 to epoch 9. Okay, so the teacher is constantly so kind of this, if you start within some strong weights of the teacher, it may not be able, because like on top of some other weight. I don't think that is a strategy if you're using like this supervision technique.
Actually, your answer gave us same similar and other self-supervision. So your answer gave me a little bit of pieces that might be working. So I will tell you what I might be. So or what is that comparing what is a student that is the current features with the average of all the previous features that is the teacher, because if we like as I mentioned, if we may the teacher itself might be actually represent an ensemble of all the versions of the student versions of the previous.
Exactly. Right.
So you're comparing both of the two sides, and what you're to do is to move that average of the models, that is the model ensemble, that is the teacher, to move its representation to be on average all the errors of the student. So enhancing the generalization. I'm not really sure if I'm phrasing it.
Yeah, exactly. I think you touched a very good point, that we are trying to enhance the whole generalization of the teacher.
Okay, I think that is a very nice idea, and yeah, I think that's kind of cool.
Yeah, I think you mentioned it really right, that what we are trying to do is we are enhancing the whole generalization of the teacher, then we transfer it for the supervised learning. Yes, I agree. I totally agree with your point here.
Okay, I don't really have any other questions. So if there's any other.
Yeah, if any other this person any questions, you can just freely ask.
Thank you, Hanan. I joined lately, so I need to listen to the record again.
Oh, okay, no problem. So it's okay. So we are talking about just how to train the ViTs on the small data sets. Because if you train a ViT, you have to first train it on a very big data set, and then you are supposed to transfer it to some small data set. So we are trying to remove the first stage, that we don't need any big data. When you train the ViT on the small data set. So that was the kind of the main theme of the paper.
Okay, that's great. Thank you.
Actually, one point came to my mind right now, Hanan, regarding the shape, the sensitivity of switching to different architectures of the kind of like, you know, so maybe you zoom in, like to know just what kind of initializations you have been trying. I see uniform here.
If you can see here, this small, I mentioned that the uniform Xavier and truncated node, and
so
grad in it was it was a NeurIPS paper. So I tried to implement in like it can be applied in any architecture, but we found that it isn't working in terms of the ViTs.
I see. Actually, I was going to ask about this. So one other thing is that the 52 with initialization. I see. We typically mostly use normal.
So yeah, I mean normally one which is truncated normal.
Actually, actually we just use exploring and other traditional problems with initialization, right? Or am I missing anything?
No, I think they are.
The reasons for this actually. That's my question.
Because we have been mostly using these initialization schemes in the CNNs, and we kind of in the VITs. The VITs are kind of sensitive to these.
The question is that why is they are so sensitive to that much?
Because I mostly think that is because the architecture of the VIT itself is a bit complex. Not very complex, but it is simple. But that simplicity makes it a bit complex in terms of it has attention layers, only the linear layers, and so when these initialization schemes came, they mostly came for the CNN architectures or for the linear layers or something like that. And when the VIT architecture came, we didn't have any separate new initialization scheme which for the VITs. Since mostly what I have seen for the VITs, as you can see here also that the scores for the normal is mostly other ones.
Yeah, I see. But one thing is that the VIT itself is built upon like these and all this stuff, and I was actually thinking that the initializations might actually as well work with it. So it might be it was actually a little bit of it is so sensitive.
Actually, that was the main motivation of our paper, that the VITs are a bit sensitive towards the weight initialization, and why we need a supervised scheme to initialize the weight of the VITs for small data sets, because we tested these schemes only on the small data sets.
Yeah, I think that's kind of cool. Okay, for me. So if Muhammad or Iman have any other questions, we can progress with them.
Yeah, sure.
I don't have any other questions. The session was amazing, and the paper was great, and the efficiency was the target.
Thank you so much.
Jazakallah khair.
Thank you, Hanan.
Thank you. It's my pleasure to be here with you people. And I thank you enough to be here and listen to me. I would be looking forward to attend more sessions like that and to people in
Yeah, absolutely. That would be great. I think we can actually stop the recording right now because we are concluding our session.
Yes, I think